All right, I think we can get started. Hello, everyone. Welcome to ethics seminar series. This is John, I'm the seminar coordinator, and together with me is Miss Kathy Medley. Kathy is our communication specialist, and today Kathy and I will be the moderator. Today we are excited to have our speaker, Dr. Kwon, joining us from Woods Hole Oceanography Institution. A few things before we get started. So this seminar is being recorded and will be later published on our YouTube channel. Please feel free to ask questions or raise your virtual hands, and Kathy will unmute you for your questions. And so let me briefly introduce the speaker before we get started. So Dr. Kwon is a senior scientist in the Physical Oceanography Department and the Woods Hole Oceanographic Institution. Prior to that, he was a postdoc in the Climate and Global Dynamics Division at the National Center for Atmospheric Research. His Ph.D. in Physical Oceanography is from the School of Oceanography at the University of Washington. His research primarily revolves around one question: what is the role of the ocean in climate? More specifically, his research focuses on the variability in the ocean and atmosphere and the interaction between the two in the extratropics on timescales of a few years to several decades. This welcome speaker, and I will hand this over to Dr. Kwon. Dr. Kwon, please proceed.
Well, thank you, John, and thank you, Cassie, for introducing me and organizing this seminar. Before I start, I'd like to ask everyone who's listening right now to just stop me for any question or any clarification during the talk. I'd rather have an active discussion rather than just quiet talk and be able to finish on time. So please stop me, especially even for this virtual format, because I cannot see any of you. I heard from John and Cassie, but other than the two, I don't even know there's any of you out there listening right now. So please interrupt and speak up so that I know you are there. With that, so my title for today's talk is Impact of Multidecadal Variability in Atlantic Sea surface Temperature on Winter Atmospheric Blocking. So let me start with just very brief introduction about atmospheric blocking, just in case some of you may not be familiar with the concept of blocking. So blocking is a low frequency weather phenomenon with large scale stationary system, in general an anticyclone, often related to extreme events. So the plot shows schematic of, on the left, to normal weather condition, which has jet stream, weather strait, and weather system progresses from west to east in about weekly time scale. When there's blocks, especially in this schematic on the eastern side of North Atlantic, it blocks the normal flow of the weather, so it diverts the jet stream and sometimes store the weather system for extended time, for a week or sometimes 2 weeks, some in extreme cases, to generate some extreme conditions. So that's the atmospheric blocking. And another side of the coin for today's talk is the Atlantic Multidecadal Variability, AMV, which is also called AMO. And it's formally defined as the detrended 10-year past-filtered annual mean area average SST anomaly over the entire North Atlantic. The exact definition varies from study to study, but this covers the frame of pre-web. So on the left-hand side, shows the AMO time series, and it shows the multi-decadal variability of alternating positive and negative phases of about 60 to 70-year periodicity. On the right-hand side, it shows the spatial pattern, which has warming for the entire Atlantic, but with the maximum warming in the subpolar gyre region. So that's the blocking and AMB, and it has very different time scale. One is in the atmosphere, low frequency weather phenomenon. The other one is in the ocean, multi-decadal climate variability. They are related. Motivation comes from this highly cited paper by Sirpa Häkkinen in 2011. In that paper, Sirpa and the collaborators showed that blocking and AMB share multi-decadal modulation. So in the plot, the black line is the number of blocking days in winter. So it fluctuates, and it has rather high frequency because it's a weather-related phenomenon. But it shows the multi-decadal modulation. And on top of that, there's two colored curves which shows the AMB time series. So the dashed line is AMB time series before detrending, and the red solid line is after detrending. So especially the red and black line shares this multi-decadal modulation over time. So the blocking and AMB apparently have this relationship in multi-decadal time scale. And of course, the question is why? So the Sirpa Häkkinen's paper mostly focused on the atmospheric circulation related blocking driving the ocean. So it was mostly blocking to AMB perspective. But at the same time, it's curious why blocking had multi-decadal modulation in the first place. The weather phenomenon, it can be just white noise, and why does it have multi-decadal modulation? So my project started with that question. So the first part is AMB actually influenced the low frequency blocking. The answer is yes. So you can find in the paper published earlier this year. And there's second part, there's such relationship to blocking. Can that relationship enhance multi-decadal predictability of blocking? Another paper has been published earlier this year. So I'm going to talk about these two studies today. So before I go into those two papers, the result from those two papers, let me just lay out some background just to set the stage. So these are some of the ingredients for the North Atlantic work. That storm track blocking, rust braking, weather regimes, eddy-driven jets, NAO and AMB. So I tried to align them from high frequency to low frequency. And as some of you may know, I'm a physical oceanographer by training. So when I started this project several years ago, I had to educate myself about the atmospheric weather side of the study. And I read about these topics more and more. I realized how intrinsically related and complicatedly related are these all different components of the North Atlantic weather and climate. So to sum probably something like this. It's very complicated. But in the next few slides, I will try to highlight some of these relationships that's most relevant to the rest of my talk. So let me start with the fact that raspberry breaking it often results in a blocking. So to plot it from Tim Wooling's paper, this is just showing one event in the January of, and we are seeing a potential temperatures on surface, so-called dynamical troposphere, and there's cyclonic wave breaking happening on 21st of January. 2 days later, we see almost cut off block forming over Greenland. So the warm subtropical origin air is blocked over the Greenland as a result of cyclonic wave breaking. The second thing I would like to talk about is the close relationship between eddy-driven jet and raspberry breaking and blocking. So the jet wobbles north-south and it changes the tilting in the North Atlantic. And when North Atlantic jet, the eddy-driven jet is in its southerly position, the wave breaking happens more to the north side of the jet, vice versa. So this by Michel Riviere shows both jet, which is the shading, the gray shading, and the statistics of the wave breaking event based on the absolute vorticity. And they have this gray contour, which shows the cyclonic wave breaking, and the black contour, which is the anticyclonic wave breaking. So when the jet is in the southerly motional position, the wave breaking is happening over the subpolar side. When jet is moved northward and tilted more, the cyclonic wave breaking decreases substantially, but anticyclonic wave breaking enhances on the equator side of the jet. And this plot is formulated as composite of the negative and positive NAO days. So you can see this modulation of jet latitude and wave breaking is intrinsically related to NAO. The last piece of puzzle is the storm track activity. So as plot here shows from Novak et al., she separated the winter days into low transient eddy days, medium transient eddy days, and high transient eddy days, and just made a composite meridional profile of the angular momentum or zonal wind. So you can see when there's low transient eddy in the upstream in the maximum storm track region, you see jet is relatively positioned southward, and when there's high transient eddy activity in the upstream, the downstream shift northward. Because the transient efflux affects the baroclinicity, low-level baroclinicity affects the anisotropy of the eddies and the shifting of jet downstream. So the storm track activity changes drives the jet latitude and raspberry breaking change, and that results in the changes in the blocking frequency. So that's kind of a nutshell of the framework I'm going to use today. Oh, one last thing. The NAO is intrinsically related to all of these components, especially the blocking over Greenland or high latitude North Atlantic. So this paper by Tim Willings on the left-hand side shows composite for the negative NAO months. So you see this nice negative NAO dipole pattern, the canonical NAO pattern. And on the right-hand side, he removed all the days that are associated with the blocking over Greenland. And then you got this funny shape that's no longer canonical NAO pattern. So you can see how important this blocking, which is high pressure anomaly over the blocking, in forming the NAO mean circulation. Another way to look at it is simply look at the anti-correlation in the time series by this, the Davini et al. Paper. So the black line and the red, which is 5-year shading, is the blocking number of blocking days over Greenland. And the blue is the NAO time stage. As you can see by eye, they are highly anti-correlated, as can be inferred from the above pictures from Tim Willings' paper. So if you have more blocking over Greenland, that's usually associated with the negative NAO, vice versa. So that's it for the background. And I would like to start my story. So the part one is the try to explain whether and how AMB influenced the blocking. It's based on the data analysis of observational and journalist data. So before going into the relationships, we need to define the blocking. So I used the 2D blocking definition by Schroer et al. 2006, which is an extension of 1D definition by Tibaldi and Molteni 99. So we use daily 500 hectopascal geopotential height at each grid point. And for each blocking center, we calculate the gradient to the north and gradient to the south. So you can see from the plot right-hand side, the top panel is a composite for basic state. So you can, as we all know, the geopotential height decreases as you go forward, and there's jet. At the bottom, it's a composite for blocking, the Greenland blocking days. So you can see there's cyclonic wave breaking about to happen. And for the blocking center position, we calculate the gradient to the north and gradient to the south. And when there's blocking, gradient to the north gets steeper, so we apply that criteria. And gradient to the south actually reverses. So if those two criteria meet at the same time, we say we found instant blocking. And if that condition for the instant blocking stays 5 days or longer at a given grid point, we call that a blocking event. So that's how blocking events are detected for persistent time period. With that, we can calculate how many blocking days are there for every month and every year. And we use the 20th century analysis from 1901 to And because we are interested in this multi-decadal A and B related variability, we need a long data set. So we went to the NOAA 20 CR. But as many of you know, NOAA 20 CR is the Ensemble product. So it has 56 Ensemble members. So I did the analysis for each Ensemble member and also did it for Ensemble mean. They are very comparable, so I'm going to just show Ensemble mean-based result today. I also repeated all the analysis using the SMWF ERA 20C product, which gave consistent results. So as far as the data availability, based on available data, the result seems low. So here, and the season we are focusing on is the winter, and winter is defined from December to March. So we are looking at number of blocking days. Left-hand side is climatological mean. Right-hand side is the annual standard deviation for winter. And we see the maximum mean over the British Isles, but also there's enhanced Greenland and over the eastern subtropical ocean over the Azores. The annual standard deviation is has very similar shape to the critical mean, so it indicates the strengthening and weakening of the mean pattern rather than over shifting of the patterns. And over the Greenland, we have about 6 days amplitude of the interannual variability. If we calculate of the number of blocking days, we get these EOFs. So it goes from EOF 1, 2 to 3. And the left column is the spatial pattern of EOF. Blue is the negative anomaly, red is the positive anomaly. Each control line is 1 day. And on the right-hand side, the black line is the PC time series. And there's shading the color bar, which is NAO time series. So you can see the UF1 is seesaw between the Greenland and British Isles, and it's highly correlated with NAO, so it's dominated by interannual variability. The UF2 is the main mode of variability we are interested in for the rest of the talk. I've looked at the correlation with AMO, AMV with each EOF and each center of action for individual EOFs. It turns out that UF2 is the only and most correlated pattern with AMO, and especially the two center of actions in the UF2 that's most relevant to AMV correlation is the Greenland and over the Azores. So there's seesaw between those two high latitude and region. To look at that a little bit more closely, so here's the time of AMV, which is color shading, and blocking PC2, which is black line. The spiky ones are from yearly data, and the smooth curve is from 10-year low pass time series. And as you can see from there's already multi-decadal modulation of the blocking PC2, and you can see the correlation between AMV and PC2 is decent. Calculate lagged correlation. The left-hand side is using yearly data, and right-hand side is using the 10-year low pass data. And we can see that even unfiltered yearly time series, the maximum correlation is found when A and B lead the blocking by 3 years. And the correlation is rather asymmetric between negative and positive lags. But it's more apparent when you do the filter. Asymmetric, and there's no significant correlation when blocking leads, but there's maximum and significant correlation when A and B leads by 2 to 4 years. So found relationship between the blocking and A and B. So let's try to why we have those relationships. So I'm going to use the composite analysis rather than regression correlation, because the relationships, as I will show you shortly, is highly asymmetric between the A and B positive phase and A and B negative phase. So composite is more appropriate approach. And I'm going to use top 20 percentile and bottom 20 percentile of the A and B years to composite various states and SST. So A and B, just few things about the composite and A and B index. A and B index is calculated and detrended following Ming-Feng-Ting and Surfer-Hakkinen respective paper, which uses the same method. And for the composite, before doing any composite, we remove the tropical Indo-Pacific teleconnection by removing regressions onto the ENSO, the tropical Pacific UF1 to 3. Because tropical influence may impact the atmosphere and ocean in the extratropics at the same time, so it can give spurious correlation between the ocean and atmosphere. So we want to get rid of that possibility. Nevertheless, I also repeated the analysis without removing tropical influence, and it didn't make a big difference. I also slightly smoothed the atmospheric variable. 10-year low filtered, it's just 1-to-1 smoothed just to bump up signal to noise ratio slightly. And statistical significance based on 10,000 random permutation in 2-year blocks. So that's how I did the composite analysis. So here is a BG plot. This is a composite patterns for the winter blocking days, number of blocking days based on warm NAO years. So top 20 percentile NAO years. And let me walk you through this BG plot. So each panel shows different lag relative to NAO. So start with top left when NAO lags. So blocking leads NAO by 1 year, and then it's a simultaneous. The third one is when NAO leads blocking by 1 year, 2 year, 7 years. And again, the blue is negative anomaly, red is positive anomaly. So blue means less frequent blocking days, and red means more frequent blocking days. And the shading is significance, local significance at 5%, and I also calculate the field significance, which show by green contours. So there's two groups of patterns emerging in this plot. So first of all, there's patterns from lag -1 to +1 with the maximum British Isles. And the maximum is found when blocking leads AMO by 1 year. This is the pattern related blocking related atmospheric circulation driving AMO. And this is the pattern discussed in the Surfer-Hakkinen's 2011 paper. we are more interested in how A and B may impact blocking. So when A and B lead, there's another pattern emerges, and it's different. So there's a pattern with more blocking days over Greenland and less blocking over Azores. And that intensity lag increases up to 7, with more blocking over Greenland up to 5 days. So this explains most of the interannual variability, if you remember that the one standard deviation was 7 days. So this is the pattern we are trying to explain. And this is the pattern that projected well onto the PCUF2 pattern of blocking. So this was following A and B, the warm A and B years. We do the same thing now following the cold A and B years. So using the bottom 20 percentile. And the patterns are very different. So I left this pink from the previous just to guide you your eyes. And when we had a strong response pattern, we don't see much. Most of them are just dissipated. But actually we see different lags that show strong and opposite pattern to the previous one we saw. So from lag 0 to 2, we see this reduced blocking frequency over Greenland and enhanced blocking frequency over Azores. And it's maximum at lag 2. So there's different time evolution between the positive AMO years and following negative AMO years, which I'm going to come back after a few slides. So now we know what is the blocking pattern, anomaly pattern we want to explain. So let's start with the SST. What is the related SST pattern? So if we make the same composite for the same years for the SST, we get this AMO-like pattern with maximum warming over the subpolar ocean. And if we make the composite for turbulent surface heat flux, by the way, we have this red positive anomaly, which means anomalous heat flux from ocean to the atmosphere. So we have that positive maximized over the western subpolar ocean, and they coincide with the warmest anomaly. So when there's warmest SST anomaly, there's more heat flux from ocean to atmosphere that poses the anomalous diabatic heating in the lower atmosphere. And then what is the impact of that anomalous diabatic heating posed by ocean? That heating, the maximum heating is located in the subpolar side of the mean storm track, and it reduced the meridional gradient of the lower atmosphere. So this is the dTdy at 850 hectopascal for following the warm A and B years. So the black contour is the mean, and you can see the mean decreases towards the pole after the maximum, but there's anomalous positive anomaly that reduced the meridional gradient because of this heating. And what that does, the weaker meridional gradient is reduce the baroclinicity and reduce the transient heat flux storm track activity. So this plot shows the daily histogram of the transient heat flux at 850 over this maximum storm track region. And there's two histograms. The gray shading shows histogram for the all years, and the red one is showing the years just following warm A and B by 7 years. So you can see the probability distribution shifted towards the weaker side. To show them more clearly, when I differentiate, when I subtract the red from gray, I get this difference histogram, which clearly showing there's of high heat flux days and the increase of low heat flux days. This is for the following the warm A and B years. And the opposite is true for the cold A and B years when the different lead lag is taken account. So at the bottom, I have this chain of event again from the background, storm shadow activity to eddy-driven jet, Ross wave breaking to blocking to remind you about at the beginning. And the story fits to this chain of event. So I just showed you that the heating from ocean drives the reduced storm track activity. So this is another way of looking at that. Previously, we looked at the daily histogram. This is the seasonal mean plot of B prime T prime bar. So we have reduced heat flux over the maximum storm track region. And that's related to the shifting of jets. So this is the zonal wind at 850. The contour, black contour is the mean, and shading is anomaly clearly shows the equatorial shift, especially in the downstream. So upstream storm track activity reduction drives the downstream jet shift. Another way to look at the jet, so is again the daily statistics. The gray histogram is for the all years that shows typical tripolar structure of the North Atlantic eddy-driven jet. And the red is the composite histogram for the years lagging A and B positive for 7 years. And you see there's increase over the southerly jet days. So for these years following warm A and B, we have weaker track due to the diabatic heating posed on the subpolar side of the ocean. And then as a consequence, jet shift southward, especially in the downstream region. So that favors the Ross breaking to the north and over the Greenland. And if we look at the pressure field, it shows the typical NAO negative phase. So this is how the could influence the blocking frequency through the chain of events. Here I plot the lag correlation similar to that I showed for the blocking PC2 earlier. The A against the NAO. And as we saw before for the blocking PC2, we again see the asymmetric relationship with the peak correlation when NAO leading, both in unfiltered and low pass filtered time series. So this highly asymmetric correlation, especially in low frequency between NAO and AMB, clearly suggests the AMB drives the blocking and NAO. So a couple of questions before wrapping up this part. So I showed you it takes about 3 to 7 years following the warm AMB years to see the blocking response pattern to emerge. And why does it take so long? And just I want to make it clear that I'm not suggesting that it takes atmosphere so long to react to the ocean anomaly. Actually, atmosphere react to the ocean anomaly very quickly in 2 weeks to 2 months time scale. And 3 to 7 years is just too long for the atmospheric time scale. It's rather an oceanic time scale. And it's probably due to the evolution of A and B anomaly, which is related to the ocean circulation. So A and B anomaly is not static anomaly. It evolves in time, of course. And this plot shows the SST composite reference to the warm A and B years. As you can see, the warmest anomaly slowly propagates into the subpolar side. And as you move to the subpolar side, it's probably becoming more optimal to perturb the meridional gradient of the atmosphere. So there's some pattern that's more optimally situated to perturb the atmosphere, and it takes ocean to generate the pattern, and it takes about 3 to 7 years. Another question is going back to the fact that we saw very different between the response to the warm A and B and response to the cold A and B. And that difference is also related to the very different SST evolution related to A and B. So previously, in the previous slide, you saw warm A and B evolution. Here I'm showing you cold A and B SST evolution. Year when A by about 1 year, and then it dissipates rather quickly compared to the warm A and B years. So when there's a maximum SST anomaly, you do see the maximum blocking response. So it's again related to the evolution of SST and probably related to the ocean, but I haven't gone into detail how ocean changes and how ocean circulation makes this evolution in SST. So that's maybe for the next talk in a couple of years. So the summary of the part 1. So I talked about how A and B influence the atmosphere. And in positive A and B case, about 3 to 7 years later, we saw more blocking over Greenland and less blocking over Azores and negative NAO. And this is consistent with multiple previous studies. Especially most of these studies looked at the A and B to NAO relationship. So only one of them looked at the blocking, and most of them were modeling studies. So our study was based on the reanalysis and observational data, so it can maybe act as a benchmark for modeling studies. But what's more interesting is all these studies differ in the actual mechanism. They all show similar end result, having negative NAO following the positive A and B. But in terms of mechanism, some of them invoke mid-latitude tropospheric dynamics, as I just talked about. Some of them emphasize the role of stratosphere. Some of these studies exclusively attribute to the tropical Atlantic, and there's almost no role for the extratropical Atlantic. So they are all over. So again, perhaps our more observational-based study can provide some benchmarks. So mechanism we invoked is SST anomaly evolves over time, and when there's a maximum anomaly over subpolar gyre, there's damping of that anomaly by surface flux, which reduces the atmospheric meridional temperature gradient and weakens the low-level volcanicity and storm shadow activity that act to shift the ad-driven jet downstream. and more frequent blocking is found over Greenland and less over Azores. And again, there is strong asymmetry in the evolution of SST and resulting blocking response between A and B positive and negative years. So that's part one. And is there any question before I go to part two? Maybe not. Just want to save the question to the end. Okay, if not, I move on to the part two. So given the relationship from A and B to blocking or NAO, can that relationship enhance the multi-year predictability of blocking and NAO? And as I already said, the answer is yes. And it's detailed in this paper published earlier this year. So in this paper, we use the community Earth system model, decadal prediction large ensemble, CSMDPLE, and Steve Yeager's 2018 BAMS paper explains that showcases some of the results from that ensemble. So it is, in a nutshell, it's a retrospective multi-year prediction experiment using a fully coupled climate model, meaning there's ocean, atmosphere, land, sea ice, fully active and coupled to each other. And it's a large ensemble, so it has 40 ensemble members, which is very large considering CME5 required only 5 members from each modeling center to be able to submit a decadal prediction runs. So 40 is very large size. And it's a prediction experiment, so it needs an initialization with the best guess of the observed state. So the CSMDPLE was initialized on each November 1st from 1954 to 2015. So it has 62 different start dates. And for each start date, once it's initialized for each member, the simulation was done for 10 years and 2 months in prediction mode. So each start date and each member generated 1 to 10 year prediction. And from each member and each ensemble, you can pick 1 year predictions and string them together, make 1 year prediction time series, so 40 of them. And then similarly, you can pick 2 year predictions and string them, make 2 year 40 member ensemble predictions, etc., up to 10 year lead time. And one thing I would like to remind you is there's famous 40 member uninitialized CSM large ensemble that consists of hindcast and ICP 8.5 projection. So I'm going to briefly show you at the end the comparison between this uninitialized large ensemble and initialized DPLE. So again, we are focusing on winter DJFM, number of blocking days. The left-hand side is observation from Ensemble Inquiry Analysis 1. The right-hand side is the CSM DPLE. So as typical with this class of IPCC models, we have weaker blocking of high latitude North Atlantic, both in the mean and the variability. But overall, the pattern is realistic. And we're going to focus on this region called high latitude blocking region, boxed with blue box, which corresponds to the Greenland blocking region. because it's highly correlated with NAO. So this is so-called anomalous correlation coefficient skill matrix. The top is for the high latitude blocking, the bottom is for NAO. And we have looked at the scale for various combination of lead years. So as I told you, there's time series for each lead year. So we can combine them with different lead years. So y-axis shows the start lead year of that combination, and the x-axis is end lead year. So diagonal is for the single lead year, and the other combinations using the average of multiple lead year time series. So the maximum scale, the significant scale is found over a large portion of this matrix. The maximum scale is found when we combine from lead year 1 to 8. So there's X that shows the maximum the scale, which is ACC equals 0.65. The NAO shows similar scale distribution, even though maximum was found in slightly different combination. So if we take a look at the example time series when we got the maximum ACC for blocking, which is 1 to 8 year combination. So here there's lots of different curves. So let me start with the blue, which is the observation, the Ensemble anchor reanalysis, and smoothed by 8 years to correspond to 1 to 8 year average of the lead year in the prediction side. And the gray shading, I don't know whether you can see, it's very pale, but that's individual members. So there's widespread. And dashed dotted line is the ensemble mean. And between that dotted line and the blue, the correlation is 0.65. So that corresponds to this maximum in the matrix. But you can see interesting difference here. The prediction time series is much spikier than the reanalysis. The reason is reanalysis, if you do 8 year moving average, you have common years between the moving average from one to next. You are sharing 7 of them the same years. So inherently you are smoothing a lot. But when you do the lead year average for 1 to 8 years, actually it's coming from very different time series. For each lead year, for each initialization year, it's completely different time series. So even though you average over the lead years, you don't get such a smooth time series. So given the fact that the most of the predictability comes from this multi-decadal variability fluctuation, we also apply the corresponding smoothing to the DPLE ensemble mean for 7 years in this case. And this smoothed ensemble mean gives the scale of 0.88, which is remarkably high and never heard of before. You get similar story for the NAO time series. And this is, again, I would like to emphasize, this is a remarkable scale for blocking, especially I don't think there's any paper showing this high correlation with blocking and AMO in multi-year time scale, and even for NAO for the single model ensemble. And one thing we can do with this large ensemble is we can take a look at the dependence on the ensemble size. So on the left-hand side is the same skill matrix. On the right-hand side, we have ensemble size on the x-axis, on the skill on the y-axis, and there are different curves. Each color curve corresponds to the colored box in the matrix. So the top, the most brown curve is the one with the maximum scale on the left-hand side. And you can see all the scales increase as ensemble size increases. And even at 40, it's not saturated yet. And the same for the NAO. So here's the benefit of having larger ensemble, and the reason for we need even larger ensemble in the future. So 2 more slides. Where does this high predictability for blocking and NAO come from? Hopefully it's from AMV, and it is. So we did composite based on the high and low blocking years. And one season preceding that winter blocking years, we see SST pattern that looks AMV, positive AMV. And we also see the storm track and zonal wind that all fit to the story I told you in part 1. So the relationship we found in the observational analysis holds in this decadal prediction ensemble experiment, and that gives this multi-year predictability of the blocking. The last one I would like to talk about is that the externally forced signal is not doing much. So we have uninitialized CSM large ensemble, which uses identical external forcing to the DPLE. So if the scale is due to externally forced signal, it should show up in the uninitialized side, but it does not. So scale is coming from the multidecadal variability that's not related to the external forcing. So here's the summary of the whole part. The observational analysis suggested that positive AMV drives more blocking over Greenland and less blocking over Azores, which corresponds to negative NAO phase. And there's a strong asymmetry in the evolution SST and resulting blocking NAO response between the NAO positive and negative phases. And the CSM DPLE exhibits unprecedented high multi-year prediction scale in the blocking and NAO due to this relationship we saw in the observational analysis. So I think that's it. Thank you.
Thank you, Dr. Kwon. If anybody has any questions, they can raise their virtual hand by opening the participants panel. There's a little button with a hand. You can click that, or you could type your question and I can read it out loud. Oh, here's a question, an early question that I got through text. What is the role of the Gulf Stream on the wintertime North Atlantic troposphere?
That's an excellent question. So Gulf Stream, as many of you know, is associated with very strong SST gradient. And it's a boundary between the warm ocean and cold ocean. So there's differential heating across the Gulf Stream. So if you perturb Gulf Stream, that differential heating, diabatic heating to the lower atmosphere changes. So we have another paper that's showing just direct influence of Gulf Stream influence on the blocking, and we found a similar chain of events. But in this multi-decadal time scale in our analysis related to AMV, the relationship to Gulf Stream came out to be rather weak. But there's other papers like the Suman Nigam from your institution looked at the decadal time scale of AMV variability, which is tightly related to the Gulf Stream variability. So there's slightly different time scale of emphasis.
Thank you. I have another text question. what drives AMO/AMV?
That's an excellent question, and it's heatedly debated. And I think Mark Kane was the speaker of SX seminar last week.
Oh yeah, yes, that's correct.
And you probably heard one of the stories. So there's three major candidates: stochastic atmospheric noise, the ocean circulation, especially the Atlantic overturning circulation, and external forcing. And each of has 4, 5, 10 papers arguing different aspects of AMB drivers. So I'm on the ocean camp, but my graduate student working on to quantify the effect of each component. And I believe actually it's probably not proper to say a single driver. So there's to some extent all three of the acting on to drive A and B. So I think it's time to quantify the respective role of those different drivers.
Thank you. Any other questions? If I can unmute people, or they can just send me the text question. We can give them another few minutes. Oh, somebody, Zhang, I can unmute you. I think it's like they have.
Yeah, hello, very nice talk. And I have another question. And last week, and Professor King said that the NO basically driven the AMO or AMV, but you said the different story, the opposite story.
Well,
any comment about that?
Sure. Yeah, thank you for the question. So I believe Mark's stance is he initially started with Amy Clement that their initial thinking was it's the atmospheric noise that drives the AMB. But I think they shifted towards the external forcing. And as I said already, there's probably some component of AMB driven by external forcing. But the problem with that aspect is we are heavily relying on the climate models, and particularly they've been so far, not exclusively, but mostly related on CSM, large ensemble. And each model has different response to the external forcing. So CSM showed multidecadal AMO-like response to the external forcing, while other models show slightly different response. And also, it's highly sensitive to how you define those externally driven components and how you detrend that. So it's a tricky business, and I believe there's truth to each story, the component, and they like to be more quantitative and how much is driven by ocean, how much is driven by atmosphere or external forcing.
My last question is how much variance of the MV can explain the blocking high variance?
That's a good question. So it's actually quite a lot because in the observational analysis, the standard elevation will about 6 days over the block Greenland, over Greenland. The composite big on warm AMV show anomaly of 5 days, which is a significant portion of the annual variability. Decadal prediction experiment, this node is very small actually. You may have catched in one of my plots that I used the standardized time of observation and prediction because prediction is very small. So we have severe signal to noise problem in the model.
Oh, thank you.
No problem. Thank you.
Any other questions? Okay, in that case, thank you everyone for attending our seminar. Thank you, Dr. Kwon, for giving us a great talk. We'll be back next week with our regularly scheduled seminar series. Everybody have a great week.
Thank you. Bye-bye.
Thank you, Dr.
Bye.
Tan. Bye.